Okay, in this video I'd like to talk a little bit about L'Hopital's rule and improper integrals. These are two terms or two components of our Calc 2 class that we're going to see in the next week. We've seen L'Hopital's rule last year or last semester in Calculus 1, but we haven't seen any improper integrals. And these two, these two concepts are going to wrap up our unit for us this next week. Now, L'Hopital's rule is a way for us to compute limits of fractions that are in indeterminable form. Now, an indeterminate form, as described by this theorem here, states that if the limit as x approaches a of our upper function f of x is equal to the limit as x approaches a of our lower function g of x, and if both of those end up equaling 0, so in essence we've got a limit of 0 divided by 0, which is indeterminable, well, then we could try using L'Hopital's rule where we're told to use the derivative of each and calculate the limit of the new fraction generated there. Again, with the derivative of the numerator and the derivative of the denominator. Now, this theorem does go on to remind us, or I should say it initially tells us that a has to be the target of our limit, and it does have to exist on an interval where the function is differentiable. But also we can use this rule if x approaches, rather than just x approaching some number a, but we can use this as x approaches positive or negative infinity, or if x approaches some value a from the left or from the right. It is worth noting that if we find the derivative of a function f and g, and the function is still in indeterminable form, we can use the L'Hopital's rule a second time or a third time, and so on. So let's talk about a couple of examples here. In part A of example 1, we pretty quickly see that this denominator is going to go towards 0. But if we look at the numerator carefully as well, when we sub in the number 1, that also goes to 0. So since we have a fraction made up of two functions, a numerator and a denominator that both equal 0, I think this would be a good candidate for L'Hopital's rule. Now, what I don't want to happen, though, is that the derivative of that denominator end up equaling 0. That would be a cause for concern, and we'd have to try a different technique. But L'Hopital's rule does say that we can try finding the derivative of each, and that might give us a chance to answer the question about the limit. So the limit as x approaches 1 of this function divided by the second function would also be equal to the limit of the derivative of that upper function, so 3x squared plus 2x minus 2 over 1. Now we can use direct substitution because we can sub in the number 1 for x, and that comes out to be 3. So the limit as x approaches 1 of this original function by way of L'Hopital's rule is equal to 3. Now part B does the same thing. We have a limit as x approaches 0 of a numerator and a denominator. The denominator pretty clearly approaches 0, and in the numerator, same happens. We get a 0 here for the 3x, and the square root of 9 minus 3 also produces a 0. So again, this is a good candidate for L'Hopital's rule. So we have the limit as x approaches 0 in our original function, so we have to have the limit as x approaches 0 of the derivative of the numerator's function and denominator's function. Now I'm not going to generate the derivative of that numerator here in real time, but looking off screen on my notes, I've got a derivative of 3 over 2 times the square root of 9 plus 3x. And in the denominator, the derivative of x is just 1. So this looks a little bit better to work with, and if I do sub in the number 0 here, that's perfectly fine. I end up with a fraction 3 over 2 times the square root of 9, which comes out to be 3. This appears to be equal to 1/2. So the limit as x approaches 0 of this original function, again by way of L'Hopital's rule, the limit ends up being equal to 1/2. Now, L'Hopital's rule is not just reserved for limits that end up equaling 0 divided by 0, but they also work for indeterminable limits of the form infinity divided by infinity. So in this case, as we imagine what happens to the numerator and denominator as we approach infinity, well, both of them go to infinity. This numerator goes to infinity, and so does the denominator. So that's a good candidate for L'Hopital's rule. I've already taken the derivative of each, and again, we see that both of them go to infinity, both the numerator and the denominator. Well, that's okay. Since they both go to infinity here as well, then this new limit is a candidate for L'Hopital's rule as well. So we'll try it again. We'll investigate the limit as x approaches infinity, this time of 24x minus 12 and 12x. Again, both are going to approach infinity as x approaches infinity, so we'll try L'Hopital's rule one more time. Limit as x approaches infinity of 24 over 12, or in other words, 2. So that's telling me that the limit of the expression at the very beginning ends up equaling 2 by way of L'Hopital's rule. Or in other words, if I were to investigate the behavior of this function would be approaching a value of 2 as x gets larger and larger. Now, to me, that makes sense because I'm aware of our rules from pre-calc class. Our rules in pre-calc said that if I have a polynomial divided by a polynomial, a rational function, whose leading terms both have the same degree, then I could focus on just the coefficients at the front here to determine where my horizontal asymptote exists. Well, the horizontal asymptote here is going to be 2, and our limit has just confirmed that. Let's try this next example, part B. Now, for both of these trig functions, tangent and secant, as we approach pi over 2 from the left, the tangent function is on its upward curve towards infinity, so this piece approaches infinity. Infinity plus 1 is, of course, infinity. And for our secant function, we're at a point where we've reached the peak of a cosine curve, and it too will be curving upward towards infinity. So we're going to see an infinite result down here in the denominator as well. Sorry, that sketch was bad. The secant function is at a peak on top of cosine here, and this position, pi over 2, we can see that the function is increasing towards infinity. All right, so this is a good candidate for L'Hopital's rule. So if the limit of this expression as x approaches pi over 2 follows L'Hopital's rule, then I can find the limit as x approaches pi over 2 from the left of the derivative. Now, the derivative of 1, of course, is 0, and the derivative of tangent is secant squared. The derivative of secant squared, we've got to think back to our Calc 1 days. I'm sorry, the derivative of secant, not secant squared. The derivative of secant is secant x times tangent x. Well, if secant of x approached infinity as we approached pi over 2 from the left, then secant squared is also going to approach infinity. And if we've got this one approaching infinity, and we said a minute ago that tangent was approaching infinity, well, now we've got infinity there again. So infinity divided by infinity, we might want to try L'Hopital's rule once again. So let's see what happens here. We'll take the derivative of the numerator and the denominator. Although, now that I say that out loud, that doesn't sound appealing to me at all. I don't want to find the derivative of secant squared or the derivative of this product rule down here. So instead, let's use some trigonometry. I know secant squared over secant, that's going to turn into secant over tangent. And then our limit for this example of x as it approaches pi over 2, we can write secant as 1 over cosine and tangent as sine over cosine, allowing for us to cancel out our cosines, and we're left with the limit as x approaches pi over 2, as x approaches pi over 2 from the left, and we have the function 1 over sine of x. Now, you could consider this as cosecant if you'd like. For me, I'm more familiar with the trig results for our initial trigonometric functions. And as x approaches pi over 2 from the left of sine of x, well, as we get closer to pi over 2, we're approaching the number 1 here. So this tells me that the limit of 1 over sine of x as x approaches pi over 2 from the left should be equal to positive 1. So again, it's worth noting in this example we used L'Hopital's rule here to go from the first line to the second, but then we ended up using trig substitutions or simplifying using trig identities as we continue to our way down here. So a good combination of techniques worked out pretty well. And now if I follow the link that I've got in my document here, it brings us to a graph, and this is just my way of showing that the function itself doesn't look too bad, but we don't know what's happening at pi over 2. The function is undefined at pi over 2, and if I play different dots that are being created at different positions, we can see them as my x value increases as we get closer to pi over 2. But once we get to pi over 2 right here, it disappears for a brief moment. And that's, again, our way of indicating that that can't be computed at that position. I wonder what happens if I zoom in. I wonder if this graph will give us any indication that we've got a problem. So I'm just zooming in on Desmos here. I'm pinching to zoom, and I'm trying to find, yeah, it's not going to show us. Sometimes when you zoom in on these graphs at a x value that's undefined, or a function value that's undefined for a given x, you'll see the graph itself kind of behave strangely or differently, but it doesn't look like that's happening on this one. So anyway, there we go. All right, I'm going to stop the video on this one for the discussion regarding L'Hopital's rule, and I'll record another video to chat a little bit about improper integrals and how we can use limits to answer them. Thanks for watching.